Hey there everyone. Okay, we're going to do our next video notes on our gas laws, and we're going to be talking about Mr. Gay-Lussac and then the combined gas law. So Gay-Lussac takes our last two variable combinations. So Boyles did pressure volume, Charles did volume temperature, Gay-Lussac is doing pressure temperature. And a couple of things about it. It's a direct relationship just like with Charles. So that means that in our handy dandy equation, P1 over T1 equals P2 over T2. And when you're doing this, pressure doesn't have to be in any specific unit. Just make sure they're both the same unit, like atmospheres and atmospheres, etc. But don't forget our Kelvin temperature always has to be in Kelvin. So you're going to add 273 to any Celsius temperature. Our constants are our other two variables. Those will not be changing. So if we go through, and since it's a direct relationship, just like we had before, if we do something with pressure, if we increase pressure, temperature should also increase. If we decrease pressure, temperature should also decrease. Direct relationships. All right, let's go ahead and do a problem. So we have at 122 Celsius, the pressure of a sample of nitrogen gas is 1.07 atmospheres. What will the pressure be at 205 degrees Celsius, assuming constant volume and moles? So pressure is 1.07 atmospheres, just getting that from the problem. And then we have temperature at 122. Now don't forget to subtract or add 273, that's how I got 395. Alrighty, well my second set of variables, they are asking what the pressure will be, so that's my question mark. And then I am taking that sample of gas and heating it up to 205 degrees Celsius, so that's 478 Kelvin. So I see just from looking at the variables, I'm going to be using Gay-Lussac's law. Okie doke. So, just plugging and chugging, putting my pressure over my temperature, and my other pressure, my unknown pressure, over its temperature. And just like we did before, when we have these fractions, the easiest thing to do is just to cross multiply. That's the way you can never go wrong. But again, if you have a good math mind and you can solve whatever way it makes sense for you. So 395 Kelvin times P2 is equal to the product of the other two, 1.07 atmospheres and 478 Kelvin. We want to get P2 by itself. So we're going to go ahead and we will divide through by 395. And you notice when we do that, set it up like this, Kelvin cancels, and with 3 sig figs in our final answer, we get 1.29 atmospheres. Easy peasy. Okay, this next one, we're going to keep going, and if you want, at this point, pause this and try and do it on your own. Alright, so if that same container from the previous problem is unable to withstand pressure than 4 atmospheres, at what temperature would the can explode? So we are starting with the same two variables, the 1.07 atmospheres and 395 Kelvin. But now we know that we're going to reach 4 atmospheres. That's when the can is going to go boom. So they're asking what temperature. So my new pressure, that's what I want to get to. I'm asking myself, what temperature do I have to get it to be at 4 atmospheres? Alrighty. Got our handy dandy equation. Now we're going to just plug it in. 1.07 divided by 395 equals 4 over T2. And again, cross multiply. So we'll take the 4 times 395, the 1.07 times T2. And then we're going to get T2 by itself by dividing through by the 1.07 atmospheres. When you do that, ATMs go away, and we are all set to solve. And how many sig figs would this answer have? Hopefully you said 2. Rounding to 2 sig figs gives me 1500 Kelvin. Alright, that's pretty much all of the gas laws that explore 2 variables. We have one more we're going to talk about in a little bit. But now we've looked at each individual. We looked at pressure, volume, we looked at volume temperature, we looked at pressure temperature. Guess what combined gas law does? It does all 3 at once. So this is used when our 4th variable, moles, is constant, but all the other 3 are changing. So it's a brand new set of conditions all on all fronts, so we have to make sure we use the combined gas law. And again, just keep your units consistent. We're looking at PVT versus PVT, and we have a handy-dandy equation. P1 times V1 over T1, P2 times V2 over T2. And our constant is our moles. So let's do this problem. This is in your notes. What volume of a gas, the volume of a gas is 27.5 milliliters at 22 degrees Celsius and 0.974 atmospheres. What will the volume be at 15 degrees Celsius and 0.993 atm? So notice this one's easy. They're set up so all the variables are kind of together. So this is one set, and then they give us this other set, and they're asking for a volume. So that's what we're going to solve for. Let's pull those out. Handy dandy equation down there are P1, V1, and T1. And converting T1 to Celsius, you get 295. And then P2, 0.993. V2, we don't know. That's what they're asking for. And T2, 288 Kelvin. And then you're just plugging it into this handy dandy equation down here, making sure your units are consistent. So there's my P1, V1 over T1. That's going to be equal to my P2, V2 over T2. Now, it does get to start looking messy, but that's okay. Again, just cross-multiply numerator to denominator, and we'll get the linear format that's easier to see. So when I do that, I'm going to end up, here is the P1, I'm sorry, yeah, P2 times T1 times V2, etc. over here. And again, we want to get V2 by itself, so these guys, we're going to divide through by both of them to get V2 by itself. And that should say V. V2, there we go, fixed it, haha. And again, all we're doing is dividing through by those two numbers, and sig figs, we should get 3 in our final answer. And again, that should say V2. That's what happens when you copy and paste a lot. Lots of details to check. I thought I got them all. Guess not. Huh. 26.3. Oh. And my units. Milliliters. It's like, that doesn't look right. But that's why I'm a unit Nazi. In my mind, what I was doing was, I was like, does that unit make sense? The answer is no. It's a temperature unit, not a volume unit, and we're solving for volume. Okay, hopefully this next one I didn't do that, but you know, copy paste. Alright, this one is not in your notes, so if you want to take a minute, you can pause it and try it on your own. We're going to do the question right now. So once again, we are given a whole bunch of information, lots and lots of numbers, so 27.27, that's it. 0.2 atmospheres, 80 milliliters, those all go together. Ooh, and then this one asks what volume at STP. I hope you remember STP, standard temperature and pressure. They're giving you temperature and pressure in those 3 letters. So let's go ahead and pull this out. P1, 0.2, V1, 80, T1, 27, but that's really 300 Kelvin. And notice I put a decimal on the end to keep it to sig figs. P2, 1 atmosphere. Now that's an exact number at this point because it's a constant, and so it's not going to limit us for sig figs. V2, I don't know that one because they're asking for it. And then T2 is 0 degrees Celsius, which is just 273 Kelvin. Plugging it into the equation, standard stuff. P1 V1 over T1 equals P2 V2 over T2. And again, to solve, cross-multiply numerators and denominators, get the linear format. It's easier to see. When you do that, voila, 1 atmosphere times 300 Kelvin times V2 equals 0.2 atms, 80 mils, and 273 Kelvin. We're going to go through and get V2 by itself, dividing through by these two numbers that are stuck next to it. We're going to get those off so we can get V2 by itself. When we do that, atmospheres go bye-bye, Kelvin go bye-bye. Using my units, it's time to check my work, and I end up with milliliters. And I have 14.6 milliliters. Alrighty, here we go. I think that is it. So thank you for watching, and we're going to have some fun tomorrow in class.